Hello, and here is our video for the first lecture for the first homework. This homework does cover chapter 2 in our book. And in case you aren't familiar with how to get to our book, if you're in Pearson, just take out the menu, Pearson eText, and there is another button here, Open My eText Book, that you got to click, and that will open our book. The lines here, table of contents, if you want to check that out. We're going to do chapter 2 today, and starting with 2.1, Aristotle. So, Newton, Isaac Newton, 1670, when he first published his work, is when we consider really the start of physics, at least as we know it today, because he's the one that gave it some mathematical rigor in a way that we could make predictions and test them, where before Newton, physics was a philosophy, and it had word statements, not really much math to it at all, not much explanatory power, and most of that was from Aristotle, and that's what 2.1 is talking about here, kind of just the history of physics before Isaac Newton, and it's interesting. If you want to check it out, 2.1 is something I'd consider optional though, just more for your knowledge if you want to check it out. And again, it's history, but it's not the correct physics of today because Aristotle said some things that we don't recognize as true anymore. So, for instance, Aristotle said that if you push an object, it comes to rest. And you've noticed this, I'm sure, with many things in life. If you push something, it just stops. And Aristotle actually thought that's just how the universe worked. That the universe just was always conspiring to stop objects. And maybe that seemed intuitive or not, but he didn't identify any frictional force slowing objects down. He just thought that's the way the universe was. Objects just stopped. And Newton changed that idea. Newton actually said that an object in motion actually will stay in motion until some force acts on it. And now we identify that force as friction. Friction always going against the motion, trying to slow things down. And, you know, I never met Isaac Newton, but I know he checked out the planets a lot. And the planets do seem to just move forever. That they just continue in their orbits continuously, like nothing is slowing them down. So maybe part of his first law and kind of overriding Aristotle there was the planets, that they just seem to keep moving. And that leads, so there's Aristotle there, leads to Copernicus. So before Copernicus, they thought the Earth was a center, and they really liked perfect circles. And so they thought everything orbited the Earth in a nice, perfect circle, that your planet was just there. But as instruments got better in recording this data, because actually some of this this data takes years to record as you watch the planets go through the sky. But this model didn't work too well anymore. And still being fascinated with circles, they started putting circles on circles then. So as the planet went around the Earth, it also went around this circle. And then all the planets then had that. They were circles on circles. And so as the planet went around Earth, it also went around this circle. And that was a way to make this model fit better with the data they were seeing. And it did. This model worked really good because you have to remember back way when they didn't have very accurate ways to measure these things in the sky. And it was Copernicus that was the one that said, you know, all that stuff maybe is kind of cool, all those circles, but we can actually get better matches to the data if we put the sun at the center and then have the planets go around the sun. And there was no need then for those extra circles, that this model fit the data better. And eventually, with some time, Copernicus, as sun-centered model of the solar system, eventually took hold. And that's what I have to say about 2.1. Some interesting history there if you're into it. But the only thing that's really still true today is Copernicus, that the solar system has the sun at the center. So 2.1, optional. No homework there. 2.2, checking out Galileo. And I'm going to say the same thing here, that this is optional. It's more a tour of history. But there is one important thing here I would want to point out with Galileo. So Galileo, probably most known for dropping things off a leaning tower. Although it's my understanding today that it's doubt if he actually did that, meaning he might have had somebody else do it for him. But what he discovered here that is true today, and is that when he dropped objects of different mass, that they both accelerated down at the same rate. And that was a discovery at the time. You know, it may seem intuitive that this larger object maybe accelerates at a faster rate, but it didn't matter. And today, we identify this acceleration as gravity. Gravity causes objects to accelerate to the Earth, and the gravitational field has the same acceleration around here. And so we label that with G, very common to use, lowercase g, for the acceleration due to the gravitational field of Earth. And all the planets have different values of G because of their different masses. The mass of the planet ultimately controls how strong this gravitational force is. Technically, it's closer to 9.8, but I noticed with our book, they like to just round this up to 10, and that's cool. 10, nice simple number to use. In physics, we do use meters, M, and seconds for time. And this is then the acceleration due to gravity. And that's what's, I would think, the most important part here from Galileo is that's what he found. That the Earth had a gravitational field that acted the same on all different objects. So, let me just scroll through that. There's a picture of him. And so, I do want to mention this word, inertia, because I know inertia pops up in this section as well. What is inertia? Well, objects have a mass to them, some mass to them. And in physics, we measure that in kilograms. And this mass, this number that we assign to the mass, is a measure of how resistant this object is to motion. So if I push on a tiny object, that's easy to move. But if I push on a heavier object, something more massive, that's harder to move. Mass is a quantity that gives us a way to determine how resistant is this to motion. If I want to push it, how resistant is that? And so more massive objects are more resistant to motion. Overall, this is called inertial mass. And that's what you're just talking about here, inertia, that an object has mass. This is also sometimes called the inertial mass of an object. And this is a measure of how resistant it is to motion. So I know they just say the word inertia here, but inertial mass is what we tend to call mass that's moving. And back with Einstein, they actually talked about gravitational mass. And even with Newton, they debated if there were two types of mass, like if mass was different and how it affected motion versus how the gravitational field. There used to be gravitational mass and inertial mass. And Now we just call that mass. It's all seen the same now. And that is what I have to say about Galileo. So, optional again, 2.2 and 2.3, Newton's first law of motion. So, now we're getting into modern physics with Newton. So, that stuff, history, interesting. Newton is really where modern physics begins, though. So, Newton's first law, that an object in motion will stay in motion unless there's force acting upon it to slow it down. And now with here, they're very specific with their words. They say by a net external force. So that's actually being very specific. And what they mean is, let's say if I just have a block sliding along, that if you push on the block this way, and if you push on the block this way, and these are the same magnitude, same strengths, well, they'll cancel each other out then. And then that won't affect the motion. So when they're being very specific here by saying net external force, they're saying there's some external force coming from the outside. And that if you add all these external forces together, they don't equal zero. And then there's some net resultant force that then will act on the object to change its direction. So they're being very specific there. But usually what happens is, you got an object sliding, and the force that slows it down is friction pushing against it. So most of the time, when things are sliding, there's just one force acting against that, and that's friction. And that is what they're talking about here in this chapter, in this section here. We're going to get to some more meaty stuff going forward, but I do want to talk about the sum of forces equals zero that you're going to read here in 2.3. But I first want to talk about what's going to happen here in 2.4. So 2.4 is really where physics, in a sense, is beginning, if you want to think of it that way. So the first thing that we need to do when describing motion is to be able to talk about things with a direction. So if I say to you, travel 10 miles east, well, those are words you can understand. If I have north, south, east, and west, okay, I'll travel 10 miles east. But with physics, we'd like to express that in a way with math. And this isn't something you need for the homework, just trying to explain where the idea comes from here. But we do use a Cartesian coordinate system, standard type of XY there. And in math, left and right motion, we actually give this symbol. And it is called I hat. Like it has a little hat on it. And the hat just simply means that your direction is to the right. So if I want to draw I hat, it's just this little arrow right here. It has length 1 and it points to the right. And if I want this arrow to point to the left, well, then that's minus I hat. It points 1 unit to the left. And I hat is defined as length 1. So if I want to go 10 miles east, well, it means I want to go to the right, which would be I hat, and I want to do that for 10 miles. So I would write that as 10I in math. And this is what we call then a vector. So a vector is kind of above a number in the hierarchy of information, because a number just tells you the quantity of something, where the vector tells you a quantity, 10, and a direction to the right. And if I want to say to the left, well, I can just throw a minus sign on that, and that now means 10 miles west if we want to look at a compass. Now, for us, we're not going to need the rigors of this notation, but we are going to talk about things more of an up-down, vertical, and a left-right that's horizontal. So we're not going to use this full math notation, but we are going to split things into these dimensions. So going forward, thinking about this stuff, we will mostly be dealing in 2 dimensions. And think of, x to the right, y up. And we're going to break motion into these 2 things. So, for instance, what if I want to travel at an angle? Well, if I do that, let's say I want to travel to this point here, and now I'm at some angle. Well, that means I went some distance this way and some distance this way. And if we just use our standard, type of compass, north, south, east, and west, and I'm just going to make up some numbers here, but let's say we went 10 east. That's the length then of that arrow in that direction, 10. And then maybe I go 20 north. And then that would be the length of this arrow. So 10 east, 20 north. And then what we're really interested in now is, well, what is your actual displacement from where you started? So if you start at A and you end over here at B, well, what distance is that really? Because in physics, we're really more concerned with what is the distance between your start and your stop. And we commonly call this displacement versus distance traveled. So let's say you actually walked 10 east and 20 north. And let's just say these are miles. If you did that, well, 10 miles and 20 miles would be 30 miles. That would be your distance traveled. You traveled 30 miles. That's how much you walked out or drove or whatever. But the actual distance from your start to finish, we can get with the Pythagorean theorem. And this will be a piece of math that you'll need for the homework. And the Pythagorean theorem, if we have a triangle, a squared plus b squared equals c squared. And the really important thing here to remember is c is always the longer line, the hypotenuse. It's always, there's no exceptions. C is always that longer line. And then how you choose A and B doesn't matter, as long as you're consistent in your problem. But A and B doesn't matter. C must be the longest leg. And as long as you have C as the longest leg, you'll always be good with using the Pythagorean theorem. So if I wanted to know how far it is between A and B, I would just use Pythagorean theorem on this right triangle. So if I'm calling A 10 and B 20, well, then we can figure out what C would be, the actual distance between A and B. And that is displacement, something we're usually looking for in physics. We don't deal with distance traveled too much. In terms, though, so with all that said about position, coming here to 2.4, they're actually talking about forces here. And a force is pushing on something. Like if you go shopping and push on your cart, that push is a force. Pulling on things is a force. Maybe you have a rope attached to something. You pull a wagon. That's applying a force. You're pulling. Earth's gravitational field is a force, always pulling us towards the Earth. And then the ground from the Earth supports us. We call that a normal force. And you're not going to necessarily need to know or label these forces because they'll be given to you. But you do need to know how to add them together and maybe give what a net force is. So this picture here, showing just this girl hanging. She's just hanging there. And they're saying that her weight from the Earth's gravitational field is pulling down at 300. Now this N is the unit for force. Call it newtons in honor of Isaac Newton. In American units, we'd call this pounds. 300 pounds does not equal 300 newtons. There is a conversion there. But we will use newtons is what's used in physics. So the force pulling the girl down is the gravitational field. That force is pulling the girl down. But she's hanging onto this rope. And that rope has a tension going up. And if she's just hanging there, if she's not moving, then this rope going up must also be 300 newtons so that these add together and cancel out. So just to say this roughly or really quick with math, this force here, we would write this as 300 J hat. J actually means up and down. This, because it's pointing down, we would call this minus J hat. Again, because the minus sign means it's pointing down, we're using standard type of coordinate system. To the right is positive, to the up or going up is positive. So this going down, we consider negative. And then when we add these together, 300 minus 300 equals 0, meaning that there's no force acting on this girl, and so she's not going to move. If we just scroll down here, past the girl here, they show this yellow box and trying to illustrate these ideas more. That in this first picture, we get 2 pulling to the right. Now, I don't know what's happening there. They're just arrows. But 2 things are being pulled to the right, each at 5 newtons. So I have, let's say, someone pulling this and someone pulling this. They're both pulling with 5 newtons. Well, they're both positive to the right. So when we add these together, they'll add to be a total of 10 because they're both going in the same direction, both positive. So they're going to add to be 10. And that's the picture they're showing over here then. So they have applied forces and then the net force. The net force simply means I'm adding all the forces together. The second picture, we got maybe somebody pulling to the right and then maybe somebody pulling to the left. And now with math, we write this as then a positive 5 because it's to the right. But this is to the left. And so we'd actually call that a minus 5 once we give it the vector notation. But it's all right to think of here as left and right. Think of right as positive, left as negative, up as positive, down as negative. So that when we add these forces together, 5 minus 5 then would get us 0. And that's what they're showing in this next picture here, that the net force is 0. That when we add these 2 forces together, they cancel each other out. And in the final picture, we got 10 to the right, and then 5 to the left. And again, if we wrote this with math, we'd say this is positive 10, this is minus 5, again, to the left, considered minus. And so when we add these together, we'd get a total resultant force, a total net force of 5. And again, that's what they're showing in this other picture here. And this is adding forces together. I just want to say really quick, In doing this, we didn't have to talk about what these forces were. I'm just made the analogy that maybe there are people pulling on this block. But that's how general it is here. Just talking about if we have forces on an object, if we want to know how that object is going to move, then we have to add all those forces together. So, if I have some object in space and there's all these forces maybe pushing and pulling on it, well, if we want to know how this object's going to move through space, then we have to add all these forces together. And if we add all these forces together, maybe we'll get 0, which means the object's just going to stay there. Or maybe there's some resultant force that then pushes it along the motion it's going. And if we scroll down here, here's where they're just mentioning Pythagorean theorem on, you want to know some math that's going to be needed. Make sure you got Pythagorean theorem written down. A squared plus b squared equals c squared. And what do I want to say, though, is really about this statement here. An awesome rule of nature. And let me first explain this notation before I explain why I'm focusing on this statement. So don't freak out about the math. Nothing hardcore here. The summation symbol is something that is used in some pretty hardcore math, but we're only using it for the word. We're using this to mean sum. And so in physics, for this case right here, we don't use the symbol too rigorously. Mathematicians not always happy with that. But in physics, for this part here with Newton's laws, we really just use this as meaning the word sum. So we're going to sum together all of the forces. And that's what that math notation means. Look at your object, sum together, add together all the forces, and that's what Newton wants you to do. Now, Newton said, so Newton's first law is an object will continue in motion unless there's a net force acting upon it. That's Newton's first law. Newton's second law is that the sum of forces equals the mass of that object and then the acceleration of that object. And this is Newton's second law. Again, the first, an object in motion stays in motion. The second is the sum of forces equals mass times the acceleration. And this, I would argue to you as well as other physics people, this is the rule of nature. The rule of nature here is that the sum of forces is equal to the mass of your object times the acceleration of your object. Whereas our book is saying that the sum of forces equals 0 is the rule of nature. And I think that's going to give you the wrong idea here. And I'm going to explain why, because it affects your homework and a few things that are going to be talked about here in our text. So we're not going to deal with acceleration too much. There's a few problems that do, but for now, talking about sum of forces, the acceleration is 0. Now, when the acceleration is 0, then the sum of forces equals 0. And only when acceleration is 0. So that's the statement they're making in our book, is that the sum of forces can equal 0. It's not guaranteed. Newton's second law says it may. So this is a special case. The sum of forces equals 0 is a special case when there's no acceleration. And what can be a little confusing here is that there's two cases when this can occur. So acceleration equals 0 means the sum of forces equals 0. This can occur if your velocity is 0, which means you're standing still. So like my pen's just sitting there. It has no velocity and it has 0 acceleration. It's just sitting there. And we call this then a static equilibrium. That this is an equilibrium state because it's just sitting there and it's static. It's not moving. Now what we call equilibrium here is exactly when acceleration equals 0. And again, there's two cases. One is the static case. I have no motion. The other case, where we can have the sum of forces equal 0, is where velocity is constant. So acceleration is your change in velocity. But if there's no acceleration, then your velocity won't change. So there's two conditions that satisfy this statement. One is static, nothing's moving, it's just sitting there in my pen. The other case, though, is when you have constant motion. So for instance, if I push my pen at a constant motion, this is the sum of forces being 0. Because in order to achieve constant motion, I have to push at exactly the same force as friction opposing me. So that I'm pushing on my pen like this, and then the friction, I'm trying to balance this, as a human, I'm trying to sense with my hands, and balance the friction there so that my pen moves at a constant speed. This is also sum of forces equal, and we call this dynamic. Call this a dynamic equilibrium because it's still in equilibrium because there's no acceleration, but we do have motion. Another, and this may be what's complicated here, is there's these two cases. Another good case for dynamic equilibrium is when you drive the speed limit. When you're driving your car and you push your foot on the accelerator pedal, you don't push it all the way to the floor. You hold it at some position. And that's you as a human trying to balance the frictional forces so that you drive at this constant speed that is assumably the speed limit. But when you drive and you want to try to drive, say 60 miles per hour, that's the sum of forces being 0. You're trying to maintain a constant velocity. So I'm a little worried about this mouse saying this statement. I do think it kind of gives the wrong impression here. First of all, it's not a rule. The rule, again, is actually Newton's second law, that the sum of forces equals mass times acceleration. That's the actual rule here. And then there's two special cases when acceleration is 0. We either get a static, nothing's moving, or a dynamic where something is moving, but there's no change in the velocity. And again, the best example there, I think, is driving your car at the speed limit. That's where all the forces are balanced, and you're trying to maintain a constant velocity. And we can kind of see the wording our book uses. So 2.5, what I'm going on to next, they call this the equilibrium rule. That's static. So 2.5 is going to be static equilibrium. And then 2.7, where they say here the equilibrium of moving things, this is the dynamic. So 2.5 here is sum of forces equals 0, but velocity is 0. And 2.7 is sum of forces is 0, but you have a constant velocity. So 2.7 is like then driving your car there. So if we just check out 2.5, see what they're saying. Here, just measuring the weight. So weight is from the force of gravity. We call that mg. So when you go weigh yourself, you're not actually weighing your mass, you're weighing the force from gravity that is impacting you. So if you want to weigh less, you can go to the moon, because the acceleration due to gravity is less on the moon. So even though you have the same mass, you will feel less weight on the moon, and that's because your weight ultimately is something you experience from the Earth's gravitational field. And so here they're just going through some problems. It's just some picture ideas, just throwing a little bit more forces on here. And I just want to look at this picture really fast and just give you a quick idea. If we look at this 500 newtons, so that's the measure of force, newtons. Well, that's down. That's minus 500. It's going down. This 400 is also going down. So we'd call that minus 400. This 400 is also going down. And so we'd call that minus 400. Now, if we look at the two ropes, this rope is 400 up. So we give that a positive. And then finally, this rope has 900 up. And so up we define as positive. And then this is summing the forces. So this math lingo, again, you just need to know how to say it. Sum the forces. So I'm looking at my picture. I'm just adding together all of those forces, giving them a plus or minus, depending if it's pointing up or down. And just a quick look, minus 400 plus 400 is 0. And then over here we have minus 900 plus 900. And so all of this adds to 0. And then you can see they have their big statement in red there, that sum of forces equals 0. Now, if we think about this for a moment, imagine these workers on this window cleaning apparatus or whatever. How do we know if they're just standing here? So is this piece of wood they're on, is this just sitting here? Is this static, just sitting here? Or is it moving up or down with a constant velocity? And we can't tell. So by just looking at this picture, we can't tell which state we're in. We need some more information. But they could just be hanging around, standing there, or this could be moving up or down with a constant velocity. So I just want to stress this again, that Newton said, that's his Newton's second law. This is the rule of nature, quote, quote. This is Newton's second law. And we're saying acceleration is 0, and this is how we get the statement, sum of forces is 0. And they're giving more examples of arrows pointing up and down and adding them together to get the net force so you can determine how the object's going to move. So far, 2.3, 2.4, 2.5, not optional. You're definitely going to want to read those. 2.1, 2.2. that's the history tour. Those are the optional ones. 3, 4, and 5, those are important. As well as, let me just jump to 7 really fast, because I think these almost should be together. Because again, 2.5 is static, and then 2.7 is the dynamic equilibrium, where we have things in motion, but it's constant velocity. So here they have this picture of this girl pushing a block. She's pushing, so she's pushing with 75 newtons to the right, and it turns out there's 75 newtons to the left. So when we sum these forces, we'd have a positive 75 to the right, a negative 75 to the left, and so that equals 0. So she's pushing this, and the result is a constant velocity. And, you know, I'm sure you've experienced this many times. When you go shopping and push a grocery cart, you know, for the most part, you're pushing that at a constant velocity. You know, when you push your shopping cart, do you try to keep pushing it faster and faster and faster? You know, I don't. You know, I usually find a comfortable walking speed, and I just push my cart. And I push it at this constant velocity that, you know, tends to be comfortable with your walking speed. But the point being that when you're pushing your shopping cart, and that's me pushing a shopping cart, you know, I'm pushing it in a way that just balances all the frictional forces against me, and I'm pushing it then at a constant velocity. I'm not pushing it faster and faster and faster. That would be an acceleration. So just some more examples here. Like a plane, you know, the plane has its thrust trying to push it forward, but there's air drag, that air resistance, so a frictional force that acts on the plane to slow it down. Now a plane, well, if you're taking off, if your plane's taking off, you absolutely want your thrust to be much greater than the friction. Otherwise, you're not going to take off. So they have the arrows same here, which if the airplane was already flying in the air, this is what would happen to maintain its constant velocity in the air, just like when you drive your car at a constant speed limit. But just like when you start your car from a stoplight, you do accelerate it to get it faster and faster until you reach to a point where you're comfortable with that speed limit, and then you drive at a sum of forces equals 0 because you're no longer accelerating. You're just moving at constant velocity. So plane taking off, absolutely want more forward thrust and friction so it goes off the ground. But, you know, once you're in the air, you can balance those forces and then fly at a constant velocity. So just to reiterate that again, 2.3 through 2.7, this is the important stuff that you're going to want to learn and write down. And just say it again, 2.5, sum of forces equals 0, but there's no motion. 2.7, the sum of forces equals 0, but now there's constant velocity. And I think the best example of that is driving your car. If you're having some difficulties grasping that idea, that driving your car, the forces are balanced so that you can drive at a constant speed. There's no acceleration making you faster and faster. And I skipped this 2.6, so I'm just going to come back to this and finish that off. They call this the support force. And if you scroll and read all the way to the end, the very last sentence, the very last sentence down here, then calls it what we usually call this force, and that's the normal force. So when you stand on the ground, gravity, the force of gravity, is pulling you to the ground, but you don't fall through the ground. And that ultimately has to do with all the atomic forces and the electric fields here. Very hard to break those bonds. And what this does is it creates a supporting force. So that's why they call this originally the support force. All the forces of the atomic structure when you're standing on ground or any object, all those forces are working to support you. And we usually call this the normal force. The normal force is something that's coming from the ground to support you. And whenever two objects come into contact, there's always a normal force. So for instance, even touching my hands together, it's not like my hands just pass through each other. That's because the atoms that make up my hands cause a supporting force, something that blocks my other hand from passing through it. And in this case, if I hold my hands like this, I'm going to draw my hands like this, then I have a normal force going this way. So in other words, my right hand can't pass through my left one because my left hand has a normal force stopping that. And then my left hand can't push through my right because my right hand is also giving a normal force saying, no, stop that. You're not going to go through the molecules there. So anytime objects are in contact, we say there's a normal force because the objects can't pass through each other. There's something that stops my hands just from passing right through each other. I'm not even quite sure how to do that. I guess a little optical illusion maybe. Doesn't quite look like it, but like my hands kind of pass through each other. That's not what happens because we have these forces that oppose that. And we also call that the normal force. It's perfectly fine to think of that as a support force. So, when you stand, what's supporting you? Well, it's this support force, what we would normally call the normal force, though. And they do have a picture of a book. So, if I have a table, the table is supported by the normal force from the ground. And then if I put a book on the table, the book is then supported by the normal force of the table. So the table doesn't fall through the dirt because the dirt has a normal force that supports that. And now that the table is sturdy, well, the table is also made of a bunch of atoms and molecules. And so when you put the book on it, all those atom molecules are saying, oh, nope, you can't pass through me. I'm going to stop you from passing through me. And so the table also has another normal force. So normal table, normal from the ground. And again, every time objects come into contact, we have a normal force because objects can't pass through each other. And there's a quick comment here. It's not the most important thing, but it's just kind of a thing that we talk about in physics because it's kind of slightly misunderstood, but it's really overall no big deal. But when you stand on a scale, and you measure your weight, well, the truth is you're not actually measuring your weight. What you're measuring is the normal force from the ground that's supporting you. And you can test that for yourself. So if you would go into an elevator with a scale, so you got your bathroom scale and you're in an elevator, well, if the elevator accelerates, and it does have to accelerate, so it can't be constant velocity, there must be acceleration, because acceleration leads to a force. F equals ma. If we have an acceleration, we have some net force. And if the elevator's accelerating down, you end up feeling a little bit of what? You feel lighter. And a matter of fact, if the acceleration of the elevator is the same as that of gravity, which is 10 meters per second, that's when you feel weightless. And you feel weightless. It's not that you are weightless. It's more of an illusion. You feel weightless because you no longer have contact with the ground. You know, your legs no longer have to support you. You don't feel the weight of your mass. So the scale will read less if your elevator is accelerating down. And if your elevator accelerates up, then the scale is going to read you as heavier. And again, this all has to do with the scale is actually technically measuring the normal force. And that's what we're trying to say here, that, you know, when you step on a scale, you may think you're measuring your gravitational force, which is your weight, but the scale actually reads this support force, the normal force. And that's something you can test if you go into an elevator. If you want, it may be a little strange, but if you want to go in an elevator and place a scale down and step on it while the elevator does its thing, you'll see that it reads that your weight changes. But of course, your weight isn't changing. What's changing is the normal force. And they do have a picture here of some person, and they're standing on two scales, is what's happening there. And so if we look at the forces here on this person standing on these two scales, what we have is the force of gravity, that's your weight, which again is mass, your mass times G. G is 10 for us. But the person has 2 points of contact. So there's a normal force that comes up here and a normal force that comes up here, while the force of gravity is pulling the person down. And if we sum these together, if we sum these forces, we would have normal up plus another or normal up minus the force of gravity down. And if you're just standing there, you're not moving, then your acceleration must be 0 because you're not moving. And remember, Newton's second law is the sum of forces is equal to ma. But if you're not moving, A is 0. And so we get this math statement. And what we find then is, because n plus n is 2n, and I'll just put the force of gravity on the right side of the equation there. And so what we find is that the scale reading, which is a normal force, will be then half your weight. And that's because you're standing on two scales now. And that now means you have two normal forces supporting you. Versus if you just stand on one scale, well, now you have one normal force up, you have the gravity down, and so when you sum these forces, normal up, gravity down, you're not moving, so acceleration is 0, which means this equals 0. And now this equation tells us the scale reading is your weight. So you only get the scale reading if you stand on one scale at a time. And that's what you're trying to show here with the person standing on two scales. Just to give you the idea, let you know, if you could somehow stand on 3 scales, maybe using your hand to support yourself, then the scale would read a third of what your actual weight is, because you're distributing it all over these other forces then. And finally, for chapter 2, 2.8 is, again, more for your interest. We're not going to talk about the moving Earth. We will go into motion, but no questions here from 2.8. This is more for your interest if you want to check it out. So, in conclusion here for these sections, just to be perfectly clear, 2.1 and 2, or 1, 2, and 8, I'm telling you, are optional. There's no homework questions there. It's for your interest if you find that interesting. What the homework and tests will be over is 3 through 7. 3 through 7, that's the important stuff. And just to kind of summarize what the important stuff is that Galileo, that all objects have the same acceleration. When you drop them. So let me put when dropped. And that was Galileo's big discovery, that when you drop objects, they all had the same acceleration regardless of their mass. And again, today we understand this as the gravitational field that does that. The next important thing in 2.3 is Newton's first law. An object in motion will stay in motion unless acted upon by a net external force. So that means, my object's going to just cruise along until someone comes and stops that. And in this case with my pen, that's ultimately friction that stops that motion. But that's the first law of Newton. An object in motion stays in motion. So that's what's important there. Looking at, so I guess this is section 2.2. This was 2.3. And the reason I want to label that is just to separate actually 2.5 and stuff. But just looking at 2.4, what was important there was a basic understanding of vectors. Now, you saw me use this, I don't want to write this down permanently. You saw me use like these goofy math symbols. We call this I hat and J hat. I hat represents left and right, while J hat represents up and down. That's the math lingo. What we care about, though, is just up and down and left and right. So we're not going to get into that math lingo at all. But that's what's happening 2.4 is how we're handling vectors is just with a plus or a minus sign. So we're going to use the standard idea that up is positive, and that's supposed to be a y there. Up is positive, right is positive. We're going to use the standard coordinate system. So if things point to the right, we call that positive. If things point up, we also call that positive. But if things point to the left, we call that negative. And if things point down, we also call that negative. So that's how we're going to use vectors. We're going to take just the plus and the minus sign to indicate what its direction is. And in this case, this is the up-down, and this is the left-right. That's what was important from 2.4. How do we take these arrows and write it in a math way? In a very simple math way. That if I have something that's 10 miles to the right, then I can just write that as plus 10. And to the left, minus 10. Now what I do want to connect together is 2.5 and 2.7. And the reason I want to kind of have these connect together in your brain is because this is the sum of forces stuff. So the big next thing that's important is Newton's second law, that when you add all of the forces together on an object, that will equal the mass of the object times the acceleration of that object. Now, we haven't dealt with any acceleration here because for us, the acceleration has always been 0. And that results then in the sum of forces then equals 0. It comes from Newton's second law. And in 2.5, this was static. That meant no motion. So again, that's my pen just sitting there. That's static. We have the gravitational force. So here's my pen. Gravitational force pulling it down. The table is supporting it. That's the normal force. N is up, so we give it a positive. Gravity is down, so I throw a negative on that. And that has to equal 0 because there's no motion. It's just sitting there. It has 0 acceleration. So 2.5 was the static. And then 2.7 is where they talked about the dynamic. And this is what we would call constant motion. And I think the best example of constant motion is trying to drive your car at the speed limit. Because you can all see for yourself, hey, look at me, I'm driving a constant 60 miles per hour. But you know you have your foot on the accelerator pedal. You know you're giving your car gas, that there's a force pushing you forward. And how you're able to maintain constant speed is because you have balanced with your foot on the accelerator pedal. You have balanced the frictional forces coming against you with the force from your car engine. So that's where I think some complications can be, that the sum of forces equals 0 can mean one or the other. Can't mean both. Either you're moving or you're not. So this can't mean both. It always means one or the other. And that may be something you have to determine based on the problem. And how do you know which one? No motion. That's my pencil sitting there. And then this is when you have constant motion, like driving the speed limit. And then the last thing that was important here, 2.6. So last thing I have to say for 2.6, this is the normal force. This is the force that supports you when you stand. Right now, the normal force is supporting my paper. Why is this paper not falling through my desk? Because the desk won't allow the paper to pass through it. And that ultimately comes from all the forces at the atomic level, all the things holding atoms together. Very hard to break those bonds. And so those bonds create a supporting force that prevents things from just passing through each other. And so my paper sits here on the table, supported by the normal force. All right, so lastly here, I just want to check out a few of the practice problems. So again, anything that has practice in it is not worth any points. You can do it as much as you want. It's meant for you to practice. But I want to show a few of these problems in case you'd like to see some done. And I'm just going to click the first one, see what we got. What did Galileo demonstrate in his Leaning Tower of Pisa? So this is where he was dropping things off a building. And what he found is that their acceleration was always the same. And if I look at that, that's going to be here. He demonstrated that light and heavy objects gain the same amount of speed when falling. Now we call that acceleration. They both have the same acceleration there. And that's an example of problem 1. Now again, I'm just going to skip 2 because I don't want to do all these. These are the practice problems for you to check out. This one says, how much force is required to keep a moving hockey puck in motion on a perfectly frictionless surface? So we have this hockey puck there's no friction. That's what they're saying. It's frictionless. So if there's no friction, there's nothing opposing the motion. Now, I know that may be hard to imagine because there's friction everywhere when you look around and push things. But imagine there was no friction, and that's where Newton's first law kicks in. If there's no net force acting on the object, then it will continue to move forever. So if there's no friction, then no force is required to keep it moving, because that's Newton's second law. Newton's second law is you'll have continued motion with no force. Newton's first law, an object will stay in motion unless there's some force that comes to slow it down. And if we're going to assume this is perfectly frictionless, then there's no force slowing anything down. And then the object will just continue moving forever. So how about number 5? Wants to know, what is the resultant of a pair of 1 Newton forces at right angles to each other? So a little bit of math here. So right angles means this. So very common to draw this little square box to indicate a right angle, 90 degrees. And they're saying the length of both of these are 1. And the resultant, so we started here, I'm assuming, we're ending here, A to B. The resultant is always from A to B. So there's a difference. If we go 1 to the right and 1 up, then we traveled, say, 2 miles. But that's different than just going from A to B. And same thing you're talking about here. Maybe we have 1 Newton to the right, 1 Newton up. What is the overall force then that's happening? And this is where we're going to have to use Pythagorean theorem then to figure out that hypotenuse. Make sure you have Pythagorean theorem written down, ready to use. They're telling us, now remember what's important. C must always be the hypotenuse, the longest leg. How you choose A and B doesn't matter. So I'm going to, now here they're both 1, but 1 squared plus 1 squared is C squared, because they're both lengths 1s here. So we get 2 is C squared, and then we would take the square root of both sides to find that the length would have to be then the square root of 2. And if you punch that into your calculator, you'd find that's 1.41. And that's the second result here. So square root of 2, you have to punch it into your calculator in order to see this 1.41 there. And just check it out, number 7. What is the net force on a bag pulled down by gravity with 18 newtons and pulled up by a rope with 18 newtons? So they're saying, I got this bag. The force of gravity is pulling it down. But there's a rope pulling it up. So force from the rope. And they're saying, well, this is 18 and this is 18. Now, if we wrote this mathematically, this force is up, so we'd say that positive. This force is down, so we would say that one is negative. And then when we add these together, we get 0. What I'm doing here, adding these forces together, again, this is Newton's second law. He's saying sum all of those forces, add them all up. So that's what I'm doing. I'm looking at the forces that they're giving me. I'm just adding them together. And they add to be 0. And so the net force is 0, the second option. we get the net force by adding all the forces together. And the big trick there is to making sure you include the minus sign when needed. So the minus sign used when you're going left or down. Taking a look at this one. A 12 Newton book is at rest on a flat table. Well, all right, there's my table. There's my book. How many newtons of support force does the table provide? So I have the force of gravity pulling this book down at 12 newtons. And I have some force holding it up. Now, I don't know what the number is, but I know it's up because the support force is up holding the book. So I don't know what that is. It's N, but it's positive. This 12 is pointing down, so that's negative. And the book isn't moving. The book is just sitting on the table. And so Newton says, sum all the forces together. This equals mass times acceleration. But the book is not moving, so the acceleration is 0, which then means the sum of forces. So when I added these forces together, they must equal 0 because the book's not moving. And then if we look, just move the 12 to the other side, we find then the normal force must be 12 newtons. It's the only way. There's no other way to support the book without moving. You have to have a support force of 12 newtons. Now, they say 12 newtons down. No. In this case, the support force is up. So we're going to choose 12 newtons up. And now they're asking, well, what's the net force? So two things that mean the same thing. This math lingo, sum the forces, is the net force. So two ways to express the same idea. So the sum of forces, when you add all the forces together, that is the net force. And when we added all the forces together here, we got 0. So when we add all the forces, we get 0. The net force is 0. The net force is always the sum of those forces. How about 11? If you push on a crate, all right, let me draw a crate. If I push on a crate with a horizontal force of 120 newtons, so I'm just going to say that's to the right. It could be to the left. It's not going to matter ultimately, though, how you choose it. And it slides at constant velocity. So that's very important that they say constant velocity, because that automatically means the sum of forces is 0. So they're telling us constant velocity. That automatically means Newton's second law equals 0. And then they're asking, well, how much is the friction acting on the crate? Okay. Well, now I'm going to actually add together the forces. So we're pushing to the right. There's friction opposing that motion. So when I add all the forces together, I get a positive 120 to the right. I get minus friction because that's pointing to the left. I don't know how large it is, but for certain it's pointing to the left and gets a minus sign. Now that I've added all the forces together here, there's only 2, this equals 0 because of the sum of the forces equals 0 here. And so we can just solve for friction. Friction must be then 120. And friction always opposes motion. And in this case, I have it drawn to the left. But in our choices here, they'll probably say it's the opposite. And that's why you can choose 120 to be to the right or the left here. It's not going to matter. If we look at the last one, the frictional force on the crate is 120 and opposite the direction of motion. So there's our 120, and then the opposite is telling us here it's opposite to 120. 13. If you toss a coin straight upward while riding in a train, all right, where does the coin land when the train is rounding a corner? Aha. This isn't something I talked about, so I'm glad I'm checking out these problems. Now, I did choose these problems. I just forgot that this was here. So let me just mention this quick, that there are some things we call fake forces in physics. And this is an example of one, that when you're in your car, so a top-down view, when you're in your car, Newton says an object in motion wants to stay in that motion. So you, driving your car, making this turn, your body wants to continue in its straight motion. That's Newton's first law. Your body wants to continue in the motion that it has, but you're turning your car. And so what happens is, it feels like your car or some magical force is pushing you to the side of your car. And people call this the centrifugal force, but it is overall a fictitious force, a fake force. There's no force that actually pushes you. It's more an illusion that happens from Newton's first law, that your body wants to continue straight while you turn your car underneath you, and that makes you feel like you're being pushed to the side of the car, but you're not. You're just continuing with your straight motion while your car turns underneath you. Now, if you're sitting on a very slippery seat, then you're really going to feel this effect. But if you're well glued to your seat, you'll feel your body maybe lean to the right, but you won't really slide if you have a lot of friction with your seat. But I'm sure you've all felt this if you've taken a corner pretty quickly, that you kind of feel your body pull off to the right as if something's pushing on you. But nope, that's just a result of Newton's first law. So if we toss a coin while rounding a corner, so let's say the coin is in my right hand, so I guess this is my hand. There it is. I'm tossing my coin up. But as I go to this corner here, so here's my hand again, my coin doesn't want to turn, especially if the coin is in the air. Because if it's in the air, then it has no contact with your seat. So when you throw a coin up and then you turn your car is literally turning underneath the coin. And the coin doesn't know because it's in the air. It's not in contact with your seat. So in this case, the coin will land off to the side. Now, if you weren't turning, then it'd land in your hand. But because you are turning, it will land away from your hand. Because your coin is no longer experiencing the friction with the seat. The coin has no forces acting upon it to cause it to turn. It's in the air. So it'll fall off to your side. And check out the last one. It says Lucy Lightfoot stands with one foot on one bathroom scale and her other foot in a second. And then each scale reads 375. So I mentioned this before. We got our two scales. A person standing on those two scales. That's what they look like. And so we have a normal force here, another one here, both up, and then we have gravity down. So when we sum our forces, we have up, this one's also up, but this one's down. So it gets a negative. We're just standing there, we're not moving, so this equals 0. Again, because Newton says this equals ma, but we're not moving, so a is 0. And then we get, adding the n's together, there's two of them, we get 2n minus the force of gravity. We'll throw the force of gravity to the right side. And they're telling us that the scale's reading, so the normal force is reading 375. And there's two of them. So if we multiply this together, is what then her weight actually is. So 2 times 375 will be 0, 4, 5, 6, 750 newtons is what that'll be. And most of our stuff is multiple choice, but here's an example where we would have to type a number in. And that was just 2 times 375. And so there's examples of doing some of the homework. This is the practice. The homework that's worth points is then the second item here called homework chapter 2. That's the one that's worth points. It's all these type of questions. The questions are, of course, slightly different, but it's exactly all this style of question. And if you want to practice with that, remember, check out the practice homework chapter 2. You can do that as much as you want. Not worth any points. It's for you to practice. It's optional. If you have any questions about any of this, feel free to email me, and I always try to get back to you as soon as possible. I'll talk to you in the next video.